Okay, so today we're going to look at how we can find relative extrema, but by using the second derivative test, or at least looking at our second derivatives. This is like a non-standard way, but you may be asked to use this on the AP exam, for example, when you have to check that you do indeed have relative extrema. You're going to see in future problems that I kind of do this quick check to make sure that I am talking about relative min or relative max, again in future homework problems. So this is kind of the way that I do that, and it's by using the second derivative. So after I show you this way to do the problem, I'm going to give you a summary of what I did and then what to do in case it does not work. So here we go. When we can use the second derivative to find the relative extrema, we're actually just using parts B, D, and I when we're looking at both FDT and SDT. Those are the steps that I'm referring to. So if you remember what part B is taking the first derivative, and part D is when we set this equal to 0. And we solve for x. So if we factor and set each factor equal to 0, we find that x can be 0, 1, or -1. These are our critical points. So now in part I, if you remember, this is the second derivative. So this is f double prime of x. I'm losing space here, so we write it underneath. It's negative 60x cubed plus 30x. Okay, and that's really it from here. What we're going to do is take our values we got from our critical points. And notice that it may not be all the critical points because I'm just doing part D. So it is important that you kind of go through the full analysis to do the first derivative test for your relative extrema. But once again, you may be expected to look at your second derivative for relative extrema, or perhaps this helps you on a multiple choice problem and you don't need to show the work, and this is a quicker way. So here we go. Once again, we're going to use these values into our second derivative. So if you look at f double prime of 1, and I plug in 1, 1 was an easy number to work with, so I guess I'm plugging in 1 first. I forgot the 0. We end up finding that this answer is a negative answer. Okay, so we can actually conclude, therefore, f of x has a relative max at x equals 1 because f double prime of 1 is less than 0. So you may be confused because you're saying, wait a minute, it's less than 0. What is she talking about when it says relative max? Okay, so when you look at a curve, and one in which the second derivative is less than 0, that means that your original function is concave down. You would have a relative max. Okay, so you have to understand about the concavity of curves when you're looking at, let's say, tangent lines. And so this horizontal tangent happens to be above our curve here, and that makes our relative extrema a relative max. Now, this kind of concept comes up in future problems as well to understand when we have like an overestimate, when we look at a line with our curve, or an underestimate. So this kind of gets our feet wet for that as well. So let's try another number. Let's actually try our 0 that I forgot all about. So let's say we plug in, you know what, let me just continue. There's a reason why I'm going to cut from 1 to -1 and then go back to 0. Let's say we plug in -1 into our function. So we end up with a positive answer, okay? Because this is going to be positive 60 minus 30. So therefore, f of x, you guessed it, has a relative min at x equals -1. I hope you guessed it, because f double prime of -1 was greater than 0. So it's kind of the opposite that I was describing, okay, before. So let me draw a curve like for this one. Okay, so if your second derivative is if your second derivative is greater than 0, okay, that means that f double prime is positive and that f is concave up. Well, if it's concave up and you have a tangent line where it goes concave up, this relative extrema is your relative min, okay? So that's why that is the case here. And let's go to our f double prime of 0. So since I ran out of space, I'm going to put it up here. And when I plug in 0, I'm going to notice that I don't get a greater than 0, I don't get a less than 0. I actually get 0. So there's a reason why I save this to last. When this happens from our critical points, we have to understand what's going on with our function. So we actually have to use FDT. So we did do part of FDT, but not all of it. So we'd have to come back and actually complete all of this for FDT. Okay, so I'm going to erase this and go through that and give you that summary, as I said. Make sure you get this down into your notebook so you have the problem, work, and answer. So here we go. Okay, so I added in parts A and C, and I did EFG for the first derivative test, and you can see how there is a relative min at x equals -1, okay, so that does get checked. And there is a relative max at x equals 1, so we can say check there. And you can also see that for the behavior of f, it was entirely increasing at x equals 0. So even though it's a critical point, it turns out to not be a relative extrema. If you actually continue to do the second derivative test, you find out that it is a point of inflection instead. So I'm going to pull up that slide that gives you that summary. Make sure that you jot it down. And if you're in class, we're going to have some practice problems. So good luck.